a lot. Here we go. Explain why this function has a 0 in the interval from 0 to 1. Now let's talk about what this is asking. This is a function. It's a polynomial function. What do you know about polynomial functions? Continuous where? Everywhere. Okay. Explain why it has a 0, though, between this interval. Are we talking about inputs or outputs? Input. So there's going to be an input between 0 and 1 that has an output of what? 0. In other words, I want to find f of c is equal to 0. I want to find that value c that's going to, and c is going to be between 0 and 1. So we have 0 less than or equal to c less than or equal to 1. And that value of input is going to give us an output of 0. Okay, well, let's see what happens here. Let's see, our theorem says the function is continuous on the closed interval. So, is f of x continuous on 0 to 1? Because it's a polynomial function. Absolutely. Okay. We could say f of x is a polynomial, therefore continuous everywhere. Okay. Second thing, k is any real number between f of a and f of b. What's our k down here? 0. Yes. Is 0, wait a minute, is k is any real number between f? I agree, but what do I not have down so far? So let's say k is 0, but what else do I need? What? I need f of a. What's a? And what's b? Okay, so I need f of 0. Didn't I just say it was 0? Remember, k is what? An input or an output? Output. I want to know the function's value when the input is 0, not when the output. So I need to know what's f of 0, and I need to know what's f of 1. F of 0 is how much? -2. Okay. And f of 1? 1 plus 3 is 4, minus 2 is 2. Okay. So is 0 between what? Yes. Okay. Now, I have the condition that the function is continuous everywhere in the closed interval. I have the condition that the output value, I just better write that as output here, because I know if I go back tomorrow, I may forget that that's the output. Okay? So the output is between, and these are outputs also. Okay? And this is, I'll just make output here too. Okay. So is my output between the other two outputs? Yes. Okay. So therefore, there is a value c, and we have that c is 0 less than or equal to, 0 less than or equal to c less than or equal to 1, such that, whoops, I guess I can erase, such that f of c is equal to 0. Now, why do I want it to be 0? Because it says prove that it has a 0 in there. That's what it's saying. It's telling me to prove that. Well, I have. It's continuous, and it lies between -2 and 2. Therefore, I know it's there. Take your inspires. Let's take a look at that. We can just, we'll just add another graph page. This is going to be F2 now. And we're going to put in x cubed. What was the rest of that? Plus 3x. Minus 2. crosses that input axis also is a guarantee that if it's continuous, which I know it is, it's got to have a value where its value is right there. Now I'm going to show you something. How can I prove that? Go to Menu. We haven't been here before. Some of you might have found it. Analyze Graph. You see that thing called 0? By the way, this is disconnected or unusable and press to test. So you have to show me some work there. On your 84s, you did the same thing. You had to choose a lower bound, so just place it anywhere to the left of that, and then move it over and go to the right of that value. And we see then that the answer is. Now, what does this information tell me? It tells me that the output is 0 and the input is exactly 0.596? Exactly? .596 is what I have. You don't all have that? Ah, okay. What I want you to do is go and hover on that input value. Just hover and press the plus key. Oh, I love that. Ooh. Okay. Yeah, it will increase. What happens if you press the negative key, the subtraction key? Okay, so you can increase or decrease the decimal digits. Just hover and then press that. Okay, so do you think that's the exact value? Come on, you know better than that, don't you? That's not going to be exact. That's a good close approximate, but it's not going to be exact. Let's go to insert a new page. I want to teach you something else that you might want to do. Add a calculator page. Go to Menu. Go to Algebra. We're going to solve. Some of you might have found that before. We're going to solve. Solve what? Well, let's solve x cubed plus, is it plus 3x minus 2? Do I have that in there right? Now, some of you might have said, well, why can't we just factor it? Well, it's not a quadratic, it's a cubic, so we have to be careful with that. Okay, not a quadratic, but a cubic. And when we solve, do we solve expressions? Try it and see. Press enter. What happens? Of course there's an error. You don't solve expressions, you solve what? Equations. Equals what? Now, you're going to have to, and just make it a matter of practice, put a comma and the x. X is the variable here, so put a comma x. Press enter. What do you get? Exact? No, not exact. Okay. Go to Menu, go down to Algebra, go down to Factor. Let's say you're going to factor this. So you're going to factor, I'm going to just type it in again, x cubed plus 3x minus 2. Do I put equals? Am I moving too fast? I'm just had my cup of coffee. I'm moving a little fast here, I think, but anyway. Uh-huh. Mm-hmm. But do we factor equations or expressions? So you don't want to say equals, do you? Okay. Put in a comma x. Okay. We're going to factor with respect to x. Now let's see what happens here. Oh, wow. Isn't that kind of neat? So I do have factors. Are those exact factors? No. No. Those are going to be approximate values there, not exact. Okay, but I just taught you a little bit more about the Inspire. You can use those features if you want to. But on the test, I'm more interested, on the quiz and test, on what you see graphically and how you are able to justify this using the intermediate value theorem, and can you draw me a picture that represents it? And so the picture to represent this would be something that we did over here, where you put the point there. Along with your analytical work, I would know what you mean then. Okay. Okay, I'm going to save this. And Now we're going to move to section 2.5. Okay. Now, in section 2.5, we're talking about this thing called infinite limits. There actually are two ways we can talk about infinity when we talk about limits. The other way is a section that comes up in chapter 4. And last fall, I tried to combine those two, that section in with this, and I found out we can't because there's other things that we need that we haven't studied yet, and they're in chapter 3 and the first part of chapter 4. So we can't do that. But let me just tell you, there's another opportunity to talk about limits, and it's another way of thinking about infinity with limits. This one, though, is one of those two ways. We're going to see here in just a little bit exactly what it is. Okay, so here we go. Definition of infinite limits. A limit in which the, now I never read this as f of x. Help me out. What's another name for this? Output. The limit in which the outputs of the function increases without bound. Okay, so this is our output, and then we end up then with our inputs. Our inputs approach some value c. Is c an input or an output? A limit in which the output values increase without bound as the input approaches some value c. So c would again be an input value. Okay, we say that it has an infinite limit. You have seen these before, and right down here's our connection. Vertical asymptotes. You guys have talked, we've talked in here, we've seen some already this semester, and you've talked about them in other classes, vertical asymptotes. So let's see what we've got here. If the outputs of a function approach infinity or negative infinity, as the inputs approach some input value c from right or left, then the line x equals c. What kind of a line is this? Is it a function? The eyebrows gave it away. Is x equals c a function? It's a what kind of a line? It's not horizontal. Must be vertical. Well, listen, let's think about that. If this is x equals c, it means that every point on that line has something in common. What's in common with every point? The input value is the same thing. Okay, so it's a vertical line. Is it a function? No, it definitely fails the vertical line test there. Okay, so we have that if the outputs approach infinity, meaning that we have no limit. If we're looking at this, here's my value c, and as I approach c from both directions, I have outputs going maybe there. They could also be going down here. I have outputs going maybe here, but they could also be going down here. I end up with this thing called a vertical asymptote. Why must that be dotted? What happens to an open dot in a circle? I mean, on a graph. Open dot means what? Doesn't exist? This is a line with a whole bunch of open dots. Okay? That's all it's made up of open dots. So it doesn't really exist. It's not really there. Okay, so we have this thing called a vertical asymptote. Thank you. Okay.